Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the Fourier series of an odd real function, where essentially we want to prove that any arbitrary periodic real function that is odd, call it x of t, has a Fourier series coefficient sequence c that is purely imaginary, a Fourier series coefficient that is odd, and a Fourier series coefficient when k is equals to 0 equated to 0. Now, in order to really understand what I mean by this Fourier series coefficient, I would recommend the viewer to a video that I made in the past called the Fourier series complex exponential form, clearly explained, and I've posted that video in the top right hand side corner of this video. So again, just to be clear, the three things we want to prove in this video is that the Fourier series coefficient of any arbitrary periodic real function that is odd is 1, purely imaginary, 2, odd, and 3, 0 when k is equals to 0. And before we go ahead with the proofs, I want to make a note by what I mean when I say x of t is an arbitrary periodic real function that is odd. And essentially what that means is that x of minus t is equated to minus x of t, and x of t is equated to x of t plus capital T. And an example of this is what's called the fundamental odd function example, which says that let x of t be equated to sine omega naught t. So why is this function an arbitrary periodic real function that is odd? And the reason is because if I take x of minus t, this is equals to sine of minus omega naught t, which is also equals to minus sine of omega naught t, which is equals to minus x of t. And that satisfies this condition here, saying that x of minus t is equated to minus x of t. And to prove this, we can go ahead and put in some values for sine. So say that sine of minus 0 is the same as minus sine of 0, which is equals to 0. Sine of minus pi over 2 is the same as minus sine of pi over 2, which is equals to minus 1. And sine of minus pi is the same as minus sine of pi, which is also equals to 0. So the second condition to satisfy an arbitrary periodic real function that is odd says that x of t has to equate to x of t minus capital T, or the period, the fundamental period. So we can say then if x of t is equated to sine of omega naught t, let's go ahead and calculate x of t plus capital T. This is equated to sine of omega naught t plus capital T, which is equated to sine of omega naught t plus omega naught capital T. We should note that this capital T here, t is equals to 2 pi over omega naught. So again, this is just equated to sine of omega naught t plus 2 pi, which again, if you add 2 pi to sine, you just get sine of omega naught t, which is equated to x of t. So this completes our proof to the two conditions that an arbitrary periodic real function that is odd has to satisfy. And I hope this makes sense. And if you need another example of this arbitrary periodic real function that is odd, I have done a video which I'll post on the top right hand side corner of this video called the Fourier series example clearly explained part 3, where I talk about the periodic square wave. So then in terms of my solution of the problem, we know that from the Fourier series analysis equation from our past videos, x of t is equated to this sum of k is equals to negative infinity to infinity of ck e to the minus j k omega naught t, where ck, or our Fourier series coefficient, is equated to 1 over t integral over a time period t x of t e to the minus j k omega naught t dt, where we can go ahead and write ck as this 1 over t integral from minus t over 2 to t over 2 x of t, and I'm going to write the exponential function as a cosine and sine, so cosine minus k omega naught t plus j sine minus k omega naught t dt. So then I can distribute the x of t and the integral. So then ck is equated to 1 over t integral from minus t over 2 to t over 2 x of t cosine k omega naught t. Since it's an even function, this minus sign can just become a plus. And then we get dt minus j integral from negative t over 2 to t over 2 x of t sine of k omega naught t dt. And again, same thing here. Since this is an odd function, this minus sign comes to the front here. So now going back to a video that I did in this playlist called Symmetry Properties in Orthogonal Functions, I can say then that if x of t is odd and cosine is even, right, as defined by the problem, this is going to be the integral of an odd function, because odd times even is odd, dt, which is equated to 0. And again, we know this because of that video I made in the past, and I've proven that. So please check that out before continuing this video to fully understand this concept here. And then obviously here we get this is odd and this here is odd. So then we get that an integral of an even function dt is not equals to 0. And again, I've also proven this in the video labeled Symmetry Properties in Orthogonal Functions. So therefore, we can say then that ck is equals to this 0 minus j over capital T integrated from minus t over 2 to t over 2 x of t sine k omega naught t dt. So then we can say then ck is equated to this minus 2j over t if I take the half period from 0 to t over 2 x of t sine k omega naught t dt, where x of t is real from the original question, sine is real. Again, there's no j's here or imaginary terms, so this entire integral is real, but then we're multiplying it by this minus 2j over t, and this j makes it imaginary. So then this here makes ck to be purely imaginary. Or you can say that the real part of ck is equated to 0. And that ends my proof number 1. So the second proof says that ck is odd. And in order for ck to be odd, we have to prove that c of minus k has to equate to minus ck. And essentially all we have to do is say that c of minus k is equals to minus 2j over t integrated from 0 to t over 2 x of t sine minus k omega naught t dt. Again, since this is an odd function, we can pull this negative out. So then we're left with a plus 2j over t integral from 0 to t over 2 x of t sine k omega naught t dt. And as you can see, this is equated to minus ck. So imagine putting a minus in front of this value. You would get this. All right, so I hope that makes sense. Again, this ends our proof showing that the Fourier series coefficient is odd. So then proof number 3 essentially says CO is equals to 0. And we can prove that by saying that CO is equals to minus 2j over t, integral from 0 to t over 2, x of t sine of 0 dt. Sine of 0 is simply 0. So then everything multiplies by 0. We just get 0. So that ends the proof number 3. Okay, if you have any questions or comments, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video with your colleagues and friends. And if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.